Thanks a lot, David, for the nice introduction. Actually, you should have given this talk about this letter beta. You gave a whole talk about this at a birthday party in Düsseldorf. So good morning, everybody. Welcome to the talk. Let me thank the organizers for bringing us all together here in this beautiful place and for arranging yesterday's excursion. It was really, really great. And it's my first time in Brazil. And I'm really overwhelmed by everything, the people, how friendly they are, the landscape, the country, the wideness. And so it's really great to be here. So I'm going to talk today, I'm going to focus on a particular topic, certification of non-projective measurements, that was done in collaboration with actually quite a lot of people. And so on the theory side, we worked together with Armin Tavakoli, who's in the audience, and his people from Lund. And on the experimental side, we worked together with people in Innsbruck, Martin Ringbauer and Rainer Blatt and their people. And I'm from Düsseldorf, and from the Düsseldorf side, there was involved Raphael Brinster, PhD student in my group, and Hermann Kampermann and Nikolai Widerka, senior researchers in my group. So I'm going to start, because the audience is quite broad. Actually, basically, I will spend most of the talk to define things and to bring you towards the problem that we wanted to solve. So I will remind you of what are positive operator valued measures, so general measurements. And I will also remind those of you who have never seen it about the difference between those POVMs that can be simulated by projective measurements in the same dimension of the Hilbert space, and those ones which cannot. So this is all known. And basically, we wanted to answer two questions. One question is, well, given a POVM that is not simulable, what are the POVMs that are the most strongly non-projective or non-simulable POVMs? Any guesses? If those of you who are familiar with POVMs, any conjectures? Which could be most far away from the projective ones? David doesn't want to say anything because... Okay, so if you don't have any conjectures, then let's see what happens. And then we also wanted to answer the question, well, if you have implemented a POVM in the lab, how can you actually prove that you did something more than just that could have been reached by projective measurements? So how can you witness or detect that a POVM is actually non-simulable? And there are two papers that are related to this, so a very recent PRL, published in February, I think, this year, and some preprint on the archive from last November. So let's get started. Let's start at the beginning. What is a von Neumann measurement? I think all of you know that the projective or measurement or von Neumann measurement is, sorry, I'm using the wrong buttons. A projective measurement is a set of Hermitian orthogonal projectors. And that means that if you call the operator PA, then the defining relation for a projector is that PA times PB is delta AB times PA. And the projectors sum up to the identity. And then you have certain so the index A denotes the outcome of the measurement, and the probability to find a certain outcome A is given by trace of PA times rho. So all of you know this. Then there is also state after the measurement, about which we don't care in this context. And of course, projective measurements are useful if you want to determine your state, if you want to do state tomography or QKD or state discrimination in a certain protocol called minimum error discrimination. Okay, but I think all of you also know that this is not the full story, and you can go to other tasks that can actually not be solved by using projective measurements. And the paradigm here is so-called unambiguous state discrimination, or USD. And the task is, it's an old task now, it's an old protocol. So you're given a set of two non-orthogonal states, let's call them psi and phi. And the task is to identify with a non-zero probability which one of the two states you are given, but you're not allowed to make a mistake. That's why it's called unambiguous. And just using projective measurements, this is impossible. You cannot do this task. Why not? Well, let's look at it. So here, let's look at the Bloch sphere, at the plane in the Bloch sphere, and you have given two non-orthogonal vectors. And the measurement, the projective measurement, will be indicated by these red arrows that point in opposite directions because they are orthogonal. And you see that each of these projectors has an overlap with both of the vectors. So you cannot not make a mistake. Okay, so let's go to POVMs, which are just a generalization of the projective measurements. And the only difference is now that you give up the property of projective, of being projective. So POVM, or positive operator valued measure, is again a set of Hermitian operators acting on a d-dimensional Hilbert space. And the POVM elements are positive semi-definite and they add up to the identity. And again, you have an index that denotes the outcome of the measurement, and you have a state after the measurement. And again, we are not so much interested in the state itself. So you don't have the projective property, everything else remains. And then you can do much more. So let's decompose any of these operators MA as a sum of the identity times certain prefactor, plus we are in 2 dimensions at the moment, plus a vector MA times the vector of the Pauli matrices sigma. And then in order to fulfill the requirements for a POVM, you need certain conditions. In particular, these vectors, kind of Bloch vectors for the measurement operators MA, they have to add up to 0, because otherwise you cannot fulfill the summation of the operators to be equal to the identity. So let's now look again at the same problem of USD. And what you can do now, again, you have your 2 non-orthogonal vectors, phi and psi. And what you can do now is you put one measurement operator such that it doesn't have any overlap with phi. So if you get the outcome psi, you're sure that the input state was vector psi. Another operator is called m phi because it's in the kernel of psi. It doesn't have any overlap, but it has overlap only with phi. So if you're given the output phi, you're sure that the input state was actually phi. And then you have a third measurement operator that is defined such that the sum of these 3 vectors add up to 0, as you can see in this picture. And then you can do this whole thing, and this is an old protocol, and the optimal POVM elements, so the operators in the set of in this POVM set are called POVM elements or effects or whatever you like to call them. And you see that the measurement operator on phi is 1 minus the projector onto psi and vice versa. Then you have a prefactor that has to be such that 1 minus these 2 upper operators is still positive semi-definite. And this leads to a success probability, which is 1 minus the absolute value of the overlap of the 2 vectors. So this is an old story, but it's an example for a POVM that is very useful. But we also have other very important examples of POVM. So let's for the moment focus on dimension d equal to 2. So there is a famous POVM called trine POVM, which consists of projectors onto these 3 vectors multiplied by the factor 2/3, so they are not 2 projectors anymore. And it looks like this Mercedes star in the plane of the Bloch sphere. And another very famous POVM is called SIG POVM, Symmetric Informationally Complete POVM. And it is what the name says, it's informationally complete, and it's symmetric in the sense that, again, you have a set of operators which look like projectors onto states times 1 over d, where d is the dimension of the system. And the overlap between any of these 2 vectors, which are not identical, is 1 over square root d plus 1. I mean, the absolute value of this. And for d equal to 2, there is a well-known SIG POVM, which is this tetrahedron in the Bloch sphere. Well, these POVMs have been around for a long time, and they have also been realized in experiments. Maybe one of the first experiments was done in 2015, but there are now many other experiments, so I don't even dare to write down a list because it would be for sure incomplete. Good, so these are important examples for POVMs. Well, what is a POVM, or how can a POVM be seen? I think that most of you or all of you know this anyway, so we'll go quickly. You can always see a POVM such that if you go to an enlarged Hilbert space, the so-called Naimark extension, and you add an ancilla and then you allow global operations, you can always see it as a projective measurement on a larger Hilbert space. And here is it's not unique how you do this construction. So you can either add some ancilla and then work in this higher dimensional space via the direct sum, or you can attach an ancilla via the tensor product structure. You have certain degrees of freedom how to do it, but this is all well known and the extensions are not unique. But here we don't really care about the extension, so I don't want to go in detail through these possibilities, just to remind you of what is known about PUVMs. So what I've just tried to explain to you in a very short time is that the PUVM can be seen as a von Neumann measurement or projective measurement in higher dimensions. So if you're an experimentalist and want to realize such a PUVM, what you typically do, and what was also done in the experiment that I will mention later, is that you couple your system to other degrees of freedom, and then you somehow work in this higher dimensional space. But maybe sometimes you have a system that, well, maybe doesn't have this access to higher dimensions, so you want to work in your original Hilbert space. And the question that people formulated before is, well, what happens if you don't have this resource of higher dimensions? So dimension is also a resource. If it's not available, can you then maybe simulate a given PUVM by projective measurements in the same dimensional Hilbert space? And that's the question of simulability of a PUVM. And this was, I think, first formulated in this famous paper by Michael Orzmanets, who's also somewhere in the audience maybe. And I think also Tony Assin was in this paper. So this picture is actually taken from that paper. So I ask for forgiveness because it's the best picture that you can draw for the situation. So you have an input state and you ask the question whether you can do the following. Instead of performing this PUVM, with a certain probability P1, you perform projective measurement capital P1, and then with other probabilities you perform other projective measurements. And at the end, in the third step, you're allowed to do some classical post-processing. That's the situation. And in this paper, it was already shown that we can forget about the classical post-processing because it cannot improve the scenario. So that's the concept of projectively simulable PUVM. So you don't increase the dimension, you stay in the same dimension. So let's repeat what these authors defined. So a PUVM, calligraphic M, is a set of emission operators, positive semi-definite, and we call it simulable by projective measurements if each of these measurement operators, Mi, can be written as a sum of this Pi with index k, where k is the index for the measurement. So in the picture, we had 3 measurements, 1, 2, 3. Now we can have k, and you can have as many as you want, up to n. And each of these calligraphic p with index k is a projective measurement with the rules that I explained before. And then you can ask very simple questions. So you can ask, given a PUVM, calligraphic M, can it be simulated by projective measurements or not? It's a yes-no question. And then you can also ask, how strong is the non-simulability, or how robust against noise is the non-simulability? And in this paper, people formulated a measure of non-simulability via some robustness measure. So again, I just repeat, this is still, okay, I have wanted to go back to this example and maybe ask the question for this USD PUVM that we discussed before, whether it's simulable or not. So just to look at an example is sometimes very instructive. So you've seen this picture before. And the optimal USD measurement I showed you before, it was a certain success probability. And this prefactor in front of the orthogonal state to phi was 1 over 1 plus the absolute value of the overlap. But you can also have a measurement which is non-optimal. It can be, the prefactor can be smaller than this optimal quantity. So the optimal quantity is between 1/2 and 1, just to remember this, depending on the overlap of the 2 states. And in fact, the PUVM for the optimal USD protocol is not projectively simulable. The reason is that the rank, or maybe I say it explicitly. So what you want to do is you have a vector that contains these 3 PUVM elements that I described before. And you can write it in such a way with a prefactor C, and you have in the first line, you don't have any chance but putting the orthogonal vector, psi orthogonal. And then you can put the orthogonal one to this one somewhere in these two other lines. In the second element of this vector containing the effects of the measurements, you only have the chance to put phi orthogonal, and then you can put phi projector somewhere else. And in the last term, which is a projective measurement, you can put the identity, and then you have to make sure that you reach these operators that we defined before. And as you can see from this decomposition, in the last term, you have a factor 1 minus 2c. But you have to have positive elements. So you cannot make c larger than 1/2 in order to be able to realize this decomposition. So from here, you see the way that such a decomposition works. It's just an example. And you also see that the rank of these measurement elements, these effects, plays an important role. So if there are only rank 1 measurements, then you cannot decompose it into projective measurements. Okay, so again, I put these examples that I had before, the Mercedes star and the SIG POVM, and both of them are not projectively simulable as all the effects have rank 1, and then you cannot decompose it. Good. So you cannot decompose these extremal POVMs. But what happens if you have noise? So this is again a concept introduced in the paper by Michael and Tony and others. So what they introduce is, well, let's assume that you add white noise. So it's the typical example of a depolarizing channel. So to each of the POVM elements, Mi, you add the identity. And the prefactor in front of the POVM element is called T. They called it visibility. And here in this picture, you see that T is somehow the amount of the measurement operator Mi that you have in this decomposition. And the critical visibility, T of M, is the maximum over all such T, such that the measurement is still simulable by projective measurements. It's smaller or equal to 1. So I found this very confusing when I first saw this definition, but we stuck to it because it's historically chosen in such a way. So it means that if T is equal to 1, the measurement itself is simulable. So the smaller T, the higher is its non-projectiveness. So this is something you have to remember also for the plots later. So 1 minus T, so this is 1 minus T, it's something like the distance from the set of simulable POVMs. I forgot to mention that the set of simulable POVMs is convex by definition. Or if you mix two simulable POVMs, it's again simulable. So 1 minus T quantifies the non-projectiveness. And also it was shown already that for T equal to 1 over D, any POVM becomes simulable. And then there was some other lower bounds, but at this point, there were no good upper bounds known. And so now is where our work starts, really. So I spent most of the time in explaining the setting. So let's go to the results. What did we do? We found upper bounds on this critical visibility by constructing a hierarchy of SDPs, which have a necessary condition that simulable POVMs have to fulfill. Then we picked certain highly non-simulable POVMs, like the SIG POVMs. We calculated explicit upper bounds for this critical visibility. And quite often we could show that the bound is tight by finding an explicit decomposition. So that's the main idea. And maybe one technical step, it's only one part of the technical things, but I don't want to show too much. So this is easy to grasp. So if a POVM M is projectively simulable, then we have just defined, then there exist probabilities pk and projective measurements pki such that each POVM element Mi can be decomposed into these projective measurements. And this is a necessary condition for POVM to be simulable. Okay, so from this you can construct non-negative matrices, which we call Rij, where you just append another operator pkj. And then this construction has to have a have certain properties. So for instance, you see if you sum over all I, then you get the condition that the pi k sum up to the identity. Same if you sum over j, you get mi tensor 1. Then it has to be symmetric. So if you multiply the swap operator on it and take the trace, it has to be 0. Well, also the partial transpose has to be positive, but this didn't help very much. So this means that you can formulate an SDP. You want to maximize this visibility T, fulfilling these above constraints. And as Tony explained very well in his talk, then you get upper bounds on T. So this was the program that we went through. And on the way, we also got so-called non-simulability witnesses that detect non-simulability from the dual SDP. And well, this will be, and then of course you can tensor another projector, P, L, K, etc. So you get a hierarchy of these matrices. That's what I will call the hierarchy from now on. And now I come already to the results that we achieved without putting any further details. I should have said also something more about this rank criterion, but maybe here it goes too far. So at the beginning, I asked whether anybody of you has a conjecture which POVMs might be the most strongly non-projective ones. And I think the most famous ones are the SIG POVMs that I introduced before. And they were actually conjectured in this paper that I mentioned by Michael and Tony and others to be the maximally non-projective measurements. So in the sense that 1 minus t is the biggest, that they're the furthest away from the simulable ones. And in fact, it was shown to be true for dimension 2 in this paper by Flavian Hirsch, and I think there's also Miguel Navasquez in among the authors. And they showed that this is in fact true for dimension d equal to 2 and calculated the specific critical visibility t. However, already if you go to the next dimension, d equal to 3, then we showed that this is not the case anymore. So in general, this conjecture is not true. And it's very counterintuitive. No, it's a bit surprising that you find something that you did not expect. So we also expected that the SIG POVMs in every dimension would be the most non-projective ones, but they are not. And each dimension somehow is a little bit different. So let me try to explain the outcome. So here what you see is basically, so theta parameterizes a continuous family of SIG POVMs that exists in dimension 3. And here on the vertical axis, you see the critical visibility, which unfortunately now is called V star. It was called T of M before. So this is the critical visibility. And you see that, well, all of the points on this line correspond to one SIG POVM of this continuous family. So some of these SIG POVMs are in fact have a high non-projective non-simulability. Remember again that the lower the value of the critical visibility, the higher the non-projectiveness. So these ones corresponding to the so-called Hesse SIG POVM for the angle theta equal to 0 is more non-projective than the ones on the other end for theta being equal to pi over 9. And there is a continuous range of this. So already for dimension d equal to 3, not all SIG POVMs are maximally non-projective. Good, let's go to the next dimension. D equal to 4, the situation is completely different. There's only a single SIG POVM. But we found POVMs which have a higher non-projectiveness than these ones. And also for D equal to 5 and 6, well, there we just have bounds for the critical visibility, not an exact value. But again, there exist POVMs with higher non-projectivity. And all of this is summarized in this plot here that is a little bit small, but I will try to explain what you can see here. So on the horizontal axis, you see the dimension 2, 3, 4, 5, 6. On the orthogonal axis, you see again the critical visibility. And remember, the lower the critical visibility, the higher the non-projectiveness. The black points are the SIG POVMs. So here for dimension equal to 2, everything is fine. The tetrahedron is the most, non-projective one. And then you see for d equal to 3, this is what I showed before, there is a range of critical visibilities, and there is something with the flag that is in between that I will explain in a moment. In dimension d equal to 4, the critical visibility is up here, the black point, but there are more non-projective POVMs, again with this flag. And for dimension 5 and 6, for the SIG POVMs, we just have certain bounds. So what are these flagged POVMs? So this green point with a flag 2 means that we take SIG POVM in dimension 2, and we embed it into the dimension which is written here below. So here d equal to 4. So we just embed it in that dimension, and then to make up for the dimension, we put as further effects, 2 effects in this case, which are how many? Yes, 2, to make up for the dimension. Or the flag with 3 means that we take a 3-dimensional POVM, in this case the highest non-projective one, the Hesse one, embed it into the 4-dimensional space and put another projective operator to make up. So these kind of flagged POVMs, just an embedding of the lower dimension into the higher dimension, they have a higher non-projectiveness than the SIG POVMs. So this was somehow surprising to see. And I still have maybe a few minutes to show you to address the second question that I posed. And the second one was, how do you actually certify or prove that in an experiment you did implement non-simulable POVMs? And here I mentioned very briefly that from the dual SDP you find certain operators, let us call them W for witness. So, and it's very much analogous to the entanglement scenario, which many of you know. So even the picture here was drawn for entanglement like 20 years ago. You have a convex set of simulable POVMs. The others are non-simulable, and you can find operators that describe a plane. And if the expectation value of these operators is larger or equal to 0, then it's simulable, otherwise not. And the details can be found in this paper. And in fact, it turns out that quite often you can use, well, in the examples that I showed you, for instance, for the SIG POVMs, you can, these states that make up the effects play a certain role in the witness. So you construct a witness from them, but this is not always true. Okay, so, but then how do you implement such a witness? Well, it's an operator, and you can decompose any operator into, you can write down the spectral decomposition. So you have eigenvalues lambda ik and eigenvectors. So somehow you turn around the role of the witness and the states in this scenario. So you decompose the witness operator into the states. Then the experimentalist has the task to implement these eigenvectors of the witness, which very often are the states that define the projectors, the operators in the POVM. And then you need to measure the expectation value of the measurement that you want to certify with these implemented states, lambda ik. So these expectation values can be measured in an experiment, and if you find something negative, then you have certified non-simulability, and if not, you don't know. And the experiment that was done in the Innsbruck group with ion traps, here you see a sketch of the experiment. You have one ion, calcium ion in the trap, you have certain levels. They implemented 2 different POVMs, the 2-dimensional SIG POVM that I mentioned, and a certain real valued 3-dimensional, not symmetric, but informationally complete POVM. And this was, they just have enough levels to implement these ones. And then they certify the non-simulability via a witness with a 5 sigma result. Good, and the chairman is already getting up, so I should better finish. So I've shown you that we define some symmetric extension, a hierarchy of SDPs, found upper bounds for the critical visibility, often tight, and maybe one remark that I didn't make before, if you slightly modify the hierarchy, then it is complete, so we know that it converges. And maximally non-projective measurements are not always SIG. Well, and we showed witnesses how to construct them and how to implement them in an experiment. Future directions. We believe that the hierarchy converges after a few steps, but we were not able to prove it. where can we apply these maximally non-projective POVMs? What is the role of the dimension of the ancilla if you don't allow the full dimension but smaller dimensions? And also one could extend this notion or this program, I mean, the definition has already been given, to quantum instruments. And that's all I wanted to say. Let me thank also the people in my group who did the work. There's Raphael Brinster here, Nikolai Widerka behind, and Hermann Kampermann, and well, of the other co-authors, I don't have a picture, but one of them is here in the audience, so you can look at him. Thanks for your attention.
Thank you. Any questions?
Nice talk, thank you.
Thanks.
So what you see reminds me of what happens, for instance, for states. I think I'm talking about things I did more than 20 years ago, but if I remember well, with Nicolas Gisin, we were checking what is the most robust state of non-locality. And we were taking like robustness with respect to mixing with identity. And it happened that what we found numerically, and then we understood why, was a 2-qubit maximally entangled state. Because somehow when you mix this with identity in the d-dimensional Hilbert space, well, the noise you see, somehow the noise is spread over d degrees of freedom that actually are not entangled. And I think also, if I remember well, also people have studied what is called type of separable balls or things around identity. And I think the state that gives you the best point, or the entangled state that is the closest to the identity in this sort of mixture is, if I remember well, but it's P 2-qubit maximal entangled state plus 1 minus P identity over D squared. So I have the impression that you are seeing something similar here because of your definition of robustness, which is mixing with identity in the corresponding degrees of freedom. So I think it would be nice. Okay, you're using the definition I introduced. Okay, but
so is your question what happens if you don't use the identity but something else?
Yeah, exactly.
Yes,
or you put identity
we did this also.
in the corresponding degrees of freedom.
Yes, or we did this also in a general way. This is, well, those people of you who worked on entanglement theory know that you can also define other robustness measures where you don't add the identity but something else, no? So which is called sometimes generalized robustness. So if you do this, you get qualitatively the same results. So it doesn't matter whether you choose the identity or something else.
I think the real question is 20 years ago, did he put little flags into your graphs, Nikolai and you? Okay, he doesn't want to answer. All right, maybe one more question. Richard.
Yeah, thanks for the nice talk. I'm wondering, and this might way be wrong, but what if we think about a quantum computing paradigm where we have like many qubits, and we think a bit about more modern quantum computing subroutines like mid-circuit measurements, post-measurement states, or maybe even some restricted teleportation protocols? Would this change the story?
What exactly do you want to add? I mean, we are just talking about measurements
with reduced states and adaptive protocols.
Okay, so it's a different definition of what you want to...
I still want to simulate a POVM, but I don't do it with projective measurements, but with a circuit that has mid-circuit measurements, conditional unitaries, and these things.
Very interesting question, but I cannot answer it because we didn't do it. But it's a good point.
Okay, in which case I expect a collaborative paper by Friday. And let's thank Dagmar again and move on to the next.